Cooling water corrosion damage mechanisms as a part of uniform or localized loss of thickness. Cooling water corrosion description based on API 571, general or localized corrosion of carbon steels and other metals caused by dissolved salts, gases, organic compounds or microbiological activity. Cooling water corrosion damage refers to the deterioration of metal surfaces and components that are exposed to cooling water systems, often found in industrial processes, power plants, and HVAC systems. This type of corrosion, cooling water corrosion, occurs due to several factors, including: Number 1 is chemical composition. The presence of dissolved oxygen, chlorides, and other aggressive ions in the water can significantly exacerbate corrosion rates. The pH level of the cooling water, along with temperature and conductivity, also plays a critical role in the corrosion process. Number 2 is microbiological activity. Biofilms formed by bacteria and other microorganisms can create localized areas of corrosion, known as microbiologically influenced corrosion, or MIC. These biofilms can protect underlying metal surfaces from the bulk water but can trap corrosive agents, leading to accelerated deterioration. Number 3 is galvanic corrosion. When dissimilar metals are used in cooling water systems, electrolytic reactions can occur between them, leading to accelerated corrosion of the more anodic or less noble metal. Number 4 is erosion corrosion. High-velocity flow conditions within a cooling water system can lead to erosion corrosion, where the protective oxide layer on metal surfaces is physically removed, exposing fresh metal to corrosive agents. Types and manifestations of cooling water corrosion damage mechanisms. Number 1 is pitting corrosion. This localized form of corrosion results in small, deep holes or pits in the metal, often resulting in structural failure if not monitored and mitigated. Number 2 is uniform corrosion. A more even loss of material across a surface, typically leading to thinning and eventual failure of components. Number 3 is stress corrosion cracking. This damage occurs when tensile stress is present alongside a corrosive environment, leading to the formation of cracks that can propagate and cause sudden failure. Number 4 is corrosion fatigue. Repeated stress cycles in a corrosive environment can lead to the progressive and premature failure of components, often without visible warning before failure occurs. Understanding cooling water corrosion and its implications is vital for ensuring the longevity and reliability of industrial systems that rely on these processes for temperature regulation. Cooling water corrosion affected materials based on API 571, carbon steel, all grades of stainless steel, copper, aluminum, titanium and nickel-base alloys. Cooling water corrosion damage can affect a variety of materials typically used in cooling systems, including metals, alloys, and even some non-metallic materials. The specific materials impacted often depend on the type of cooling system, the water chemistry, and the operating conditions. Here's a breakdown of the commonly affected materials. Number 1 is metals and alloys. Number A of metals and alloys is carbon steel. Commonly used due to its strength and cost-effectiveness, carbon steel is susceptible to uniform corrosion, rust formation, and pitting, especially in environments with oxygen and salts. Number B of metals and alloys is stainless steel. While stainless steel offers better corrosion resistance than carbon steel, various grades can still experience localized corrosion, such as pitting, and stress corrosion cracking, especially in chlorinated cooling waters. Number C of metals and alloys is copper and copper alloys. Copper is highly effective in heat exchangers but can be prone to corrosion, particularly in the presence of oxygen and certain chlorides. Issues like pitting and desinsification, in brass, can occur. Number D of metals and alloys is nickel alloys. These are often used in environments that are especially corrosive. Alloys like Inconel or Monel provide good resistance to pitting and SCC, but they are more expensive than other materials. Number E of metals and alloys is aluminum and aluminum alloys. Used in various cooling applications, aluminum can be susceptible to pitting and galvanic corrosion, especially in the presence of chlorides or high pH levels. Number 2 of the commonly affected materials is coated materials. Number A of coated materials, galvanized steel. while zinc coatings provide sacrificial protection, they can wear away over time, exposing the underlying steel to corrosion. Number B, of coated materials, painted or coated surfaces, protective coatings can be compromised by corrosion, leading to flaking or peeling that exposes the underlying metal to a corrosive environment. Number 3 of the commonly affected materials is nonmetallic materials. Number A, of nonmetallic materials is plastics and composites. While generally resistant to many forms of corrosion, certain plastics can degrade over time if exposed to extreme temperatures or aggressive chemicals in cooling water. Number B, of nonmetallic materials is rubber and elastomers. Used in seals and gaskets, these materials can deteriorate due to chemical exposure and temperature fluctuations in cooling systems. Number 4 of the commonly affected materials is concrete and masonry. Reinforced concrete, while not a primary component of cooling systems, concrete structures can suffer from corrosion of reinforcing steel, rebar, due to water infiltration, especially in the presence of chlorides. Cooling water corrosion affected materials. Key considerations. Number 1 corrosion type. The susceptibility of a material to corrosion can vary based on the type of corrosion, e.g., pitting, uniform, galvanic, microbiologically influenced corrosion, and the conditions present in the cooling system. Number 2 is operating conditions. Factors such as temperature, flow velocity, pH, and the concentration of dissolved oxygen and aggressive ions can significantly influence the corrosion behavior of materials. Number 3 is maintenance and monitoring. Regular upkeep and monitoring of both the materials used and the water chemistry can help in mitigating corrosion damage and prolonging the lifespan of cooling system components. In summary, a variety of metals and alloys, along with some nonmetallic materials, can be adversely affected by cooling water corrosion. Effective selection, design, and maintenance practices are crucial for managing and mitigating corrosion-related issues in cooling systems. Cooling water corrosion critical factors based on API 571. Number A, cooling water corrosion and fouling are closely related and should be considered together. Fluid temperature, type of water, fresh, brackish, salt water, and the type of cooling system, once through, open circulating, closed circulating, oxygen content, and fluid velocities are critical factors. Number B, increasing cooling water outlet temperatures and/or process side inlet temperatures tend to increase corrosion rates as well as fouling tendency. Number C, increasing oxygen content tends to increase carbon steel corrosion rates. Number D, if the process side temperature is above 140 degrees Fahrenheit, or 60 degrees Celsius, a scaling potential exists with fresh water and becomes more likely as process temperatures increase and as cooling water inlet temperatures rise. Brackish and salt water outlet temperatures above about 115 degrees Fahrenheit, or 46 degrees Celsius, may cause serious scaling. Number E, fouling may occur from mineral deposits, hardness, silt, suspended organic materials, corrosion products, mill scale, marine and microbiological growth. Number F, velocities should be high enough to minimize fouling and drop out of deposits but not so high as to cause erosion. Velocity limits depend on the tube material and water quality. Number G, low velocities can promote increased corrosion. Velocities below about 3 frames per second, or 1 meter per second, are likely to result in fouling, sedimentation and increased corrosion in fresh and brackish water systems. Accelerated corrosion can also result from dead spots or stagnant areas if cooling water is used on the shell side of condensers/coolers rather than the preferred tube side. Number H, 300 series SS can suffer pitting corrosion, crevice corrosion and SCC in fresh, brackish and salt water systems. Number I, copper or zinc alloys can suffer dezincification in fresh, brackish and salt water systems. The copper or zinc alloys can suffer SCC if any ammonia or ammonium compounds are present in the water or on the process side. Number J, ERW carbon steel may suffer severe weld and/or heated affected zone corrosion in fresh and/or brackish water. Number K, when connected to a more anodic material, titanium may suffer severe hydriding embrittlement. Generally, the problem occurs at temperatures above 180 degrees Fahrenheit, or 82 degrees Celsius, but can occur at lower temperatures. The critical factors influencing cooling water corrosion damage are essential for understanding the mechanisms behind corrosion and for implementing effective mitigation strategies. These factors can be grouped into several categories. Number 1 is water chemistry. Number A of water chemistry is pH level. The acidity or alkalinity of cooling water directly affects corrosion rates. Lower pH, acidic conditions, can accelerate corrosion, while high pH, alkaline conditions, can lead to other forms of corrosion, such as caustic cracking. Number B of water chemistry is dissolved oxygen. The presence of dissolved oxygen promotes oxidation, leading to uniform corrosion and pitting, particularly in ferrous metals. Number C of water chemistry is chlorides. Chloride ions are highly corrosive and can induce pitting and crevice corrosion, especially in stainless steels, copper, and alloys. Number D of water chemistry is conductivity and total dissolved solids. TDS. Higher conductivity and TDS can enhance the corrosive nature of water, especially when aggressive ions are present. Number E of water chemistry is hardness and alkalinity. The concentration of calcium and magnesium ions affects scaling potential and can influence corrosion behavior. Number 2 of critical factors group categories is temperature. Number A of temperature group is operating temperature. Elevated temperatures generally accelerate chemical reactions, leading to higher corrosion rates. Higher temperatures can also affect the solubility of corrosive compounds in water. Number 3 of critical factors group categories is flow characteristics. Number A, velocity. Water velocity can play a dual role. High velocities may cause erosion, corrosion, while low velocity areas may develop stagnant zones that promote localized corrosion. Number B, turbulence. Turbulent flow can elevate the mass transfer rates of corrosive agents to metal surfaces, exacerbating corrosion problems. Number 4 of critical factors group categories is material selection. Number A, material properties. The inherent corrosion resistance of materials used in cooling systems plays a critical role. Certain materials are better suited for specific environments than others. Number B, galvanic corrosion. Dissimilar metals in contact can create galvanic cells that increase corrosion rates in the more anodic material. Proper material selection and isolation can help mitigate this risk. Number 5 of critical factors group categories is microbiological influences. Number A, microbiologically influenced corrosion, or MIC. The presence of microorganisms, such as bacteria, algae, can lead to localized corrosion, often enhancing the corrosion process through biofilm formation and metabolic activities. Number 6 of the critical factors group categories is environmental conditions. Number A of the environmental conditions is oxygen levels. The amount of dissolved oxygen can vary significantly based on environmental and operational factors, affecting corrosion rates. Number B of the environmental conditions is contaminants. The presence of oils, organic substances, or other contaminants can promote corrosion and affect the performance of protective coatings. Number 7 of critical factors group categories is protective measures. Number A of protective measures is corrosion inhibitors. The use of chemical additives can help mitigate corrosion by forming protective films on metal surfaces or by neutralizing aggressive ions. Number B of protective measures is coatings and linings. Properly applied coatings can provide barriers between metal surfaces and corrosive agents, significantly reducing corrosion rates. Number 8 of the critical factors group categories is maintenance and management practices. Number A of maintenance and management practices is monitoring and inspection. Regular assessment and monitoring of water chemistry, material integrity, and system performance can help identify and address corrosion issues promptly. Number B of maintenance and management practices is system cleanliness. Maintaining clean systems by preventing biofilm, scaling, and debris buildup can reduce corrosion risks and improve efficiency. In conclusion, these critical factors interplay to determine the overall corrosivity of the cooling water environment and the extent of damage to the system's materials. A thorough understanding of these factors, combined with appropriate monitoring, material selection, and treatment strategies, is crucial in mitigating cooling water corrosion and prolonging the lifespan of cooling systems. Cooling water corrosion affected units or equipment based on API 571. Cooling water corrosion is a concern with water-cooled heat exchangers and cooling towers in all applications across all industries. Cooling water corrosion can significantly impact various types of equipment and systems across different industries. Understanding which units and equipment are most affected by corrosion can help in the implementation of effective preventive measures and maintenance strategies. Here are some of the key units and equipment that are commonly susceptible to cooling water corrosion damage. Number 1 is heat exchangers. Number A, shell and tube heat exchangers. These are particularly vulnerable due to the interaction of two fluids at different temperatures, which can lead to corrosion and fouling on both the shell and tube sides. Number B, plate heat exchangers. The thin plates can be susceptible to pitting and localized corrosion, especially when subjected to aggressive water chemistry. Number 2 of the equipment that are commonly susceptible to cooling water corrosion damage is cooling towers. Number A of cooling towers is fill media. The fill media in cooling towers can accumulate biological fouling and scale, which can hinder performance and contribute to corrosion. Number B of cooling towers is fan and structural components. Various metal structures, fans, and supports can suffer from corrosion due to exposure to humid conditions and stagnant water. Number 3 of equipment that are commonly susceptible to cooling water corrosion damage is pumps. Number A of pumps is cooling water pumps. Pump casings, impellers, and other wetted parts can corrode, especially when subjected to turbulent flow and varying velocity conditions. Number 4 of equipment that are commonly susceptible to cooling water corrosion damage is condensers. Shell and tube condensers, similar to heat exchangers, these are subjected to direct contact with cooling water, leading to corrosion of tubes and shell materials. Number 5 of equipment that are commonly susceptible to cooling water corrosion damage is chillers. Evaporators and condensers. In chillers, the evaporator and condenser tubes may corrode due to continuous exposure to cooling water. Number 6 of equipment that are commonly susceptible to cooling water corrosion damage is boilers. Feedwater and condensate systems. Cooling water used in boiler systems can introduce corrosive elements, leading to corrosion in feedwater heaters, economizers, and other interconnected components. Number 7 of equipment that are commonly susceptible to cooling water corrosion damage is piping systems. Number A of piping systems is cooling water distribution piping. Corrosion in piping can lead to leaks and failures, impacting system reliability. Number B of piping systems is connections and flanges. These areas, especially when transitioning between different materials, are prone to galvanic corrosion. Number 8 of equipment that are commonly susceptible to cooling water corrosion damage is valves. Control and isolation valves. Coatings and seals within these valves can degrade due to prolonged exposure to corrosive conditions, leading to valve failure. Number 9 of equipment that are commonly susceptible to cooling water corrosion damage is storage tanks. Water storage tanks. Tanks storing cooling water can become corroded, particularly if they have not been properly maintained or if the water chemistry is not controlled. Number 10 of equipment that are commonly susceptible to cooling water corrosion damage is instrumentation. Sensors and probes. Corrosion can affect the accuracy and reliability of sensors measuring water chemistry, temperature, and flow rates. Number 11 of equipment that are commonly susceptible to cooling water corrosion damage is heat recovery units. Heat recovery steam generators, or HRSGs in power plants. These units can be susceptible to corrosion due to the cooling water used in the heat recovery process. In conclusion, cooling water corrosion can damage a wide range of equipment, leading to reduced efficiency, potential failures, and increased operational costs. Regular monitoring, proper maintenance, and the implementation of corrosion control measures are crucial in mitigating the risks associated with cooling water corrosion in these affected units and equipment. By addressing these vulnerabilities, organizations can ensure better reliability and longevity of their cooling systems and associated infrastructure. Cooling water corrosion appearance or morphology of damage based on API 571. Number A. Cooling water corrosion can result in many different forms of damage including general corrosion, pitting corrosion, see Figure 4.81, cooling water corrosion on the ID of a CS heat exchanger tube operating at 86 degrees Fahrenheit 30 degrees Celsius, mic, stress corrosion cracking and fouling. Number B, general or uniform corrosion of carbon steel occurs when dissolved oxygen is present. Number C, localized corrosion may result from underdeposit corrosion, crevice corrosion or microbiological corrosion. Number D, deposits or crevices can lead to underdeposit or crevice corrosion of any of the affected materials. Number E, wavy or smooth corrosion at nozzle inlets or outlets and tube inlets may be due to flow-induced corrosion, erosion or abrasion. Number F, corrosion at ERW weld areas will appear as grooving along the weld fusion lines. Number G, metallurgical analysis of tube samples may be required to confirm the mode of failure. The appearance or morphology of cooling water corrosion damage can vary significantly depending on several factors, including the type of metal, the specific corrosion mechanisms at play, the characteristics of the cooling water, and the environmental conditions. Here are some common forms of corrosion damage you might observe in cooling water systems. Number 1 is uniform corrosion. Uniform corrosion appearance. Uniform corrosion leads to a consistent reduction in material thickness across the surface. It can create a dull, slightly rough texture and may result in a more matte finish. Uniform corrosion morphology. A uniform layer of corrosion products, such as oxides, can coat the surface, appearing as a general discoloration without localized pits or significant irregularities. Number 2 is pitting corrosion. Pitting corrosion appearance. Pitting corrosion is characterized by small, localized cavities or pits on the metal surface. These pits can vary in size and are often very deep relative to their diameter. Pitting corrosion morphology. The pits usually have sharp edges and may be surrounded by a brittle or flaky corrosion product. The surrounding metal may show little to no corrosion, highlighting the localized nature of this type of damage. Number 3 is crevice corrosion. Crevice corrosion appearance. Often found in areas where metal surfaces are in contact or where deposits accumulate, crevice corrosion can lead to dark, corroded areas within the crevices or joints between components. Crevice corrosion morphology. Crevices may show signs of rusting or staining. The corrosion may penetrate significantly into the metal, often more than surface examination would suggest. Number 4 is galvanic corrosion. Galvanic corrosion appearance. Galvanic corrosion can cause significant damage at the contact points between dissimilar metals, resulting in a bumpy or uneven surface. Galvanic corrosion morphology. The corroded area may have a distinct coloration due to the oxidation of the more active metal, which can develop a white, powdery corrosion product or a different colored layer depending on the metals involved. Number 5 is erosion corrosion. Erosion corrosion appearance. This form of corrosion typically presents as a rough, grooved surface where material has been removed due to abrasive action combined with corrosive attack, often around flow disturbances. Erosion corrosion morphology. Surface patterns can appear as channels or grooves running parallel to the flow direction, and there may be noticeable areas of reduced thickness. Number 6 is microbiologically influenced corrosion, or MIC. Microbiologically influenced corrosion appearance. MIC may manifest as pits or irregularly shaped holes, along with visible biofilms or a slimy appearance on the metal surface. Microbiologically influenced corrosion morphology. The presence of biofilms can be evident as dark or discolored patches, and the corrosion features might include a variety of patterns, including pitting and localized attack that resembles rusting. Number 7 is stress corrosion cracking, or SCC. Stress corrosion cracking appearance. SCC typically presents as fine cracks along the surface of the material, often in a characteristic branching or network pattern. Stress corrosion cracking morphology. Cracks may be difficult to see without magnification, but they can lead to catastrophic failures if not detected. The cracks may show intergranular features, indicating that they have traveled along grain boundaries. Number 8 is scaling and fouling. Scaling and fouling appearance. While not corrosion in the traditional sense, scaling, deposits of minerals, often accompanies corrosion issues and can lead to heat transfer inefficiencies. Scaling and fouling morphology. Scales can appear as white, crusty deposits on surfaces, which can introduce localized corrosion and create hot spots in heat-exchanging surfaces. In conclusion, the appearance and morphology of cooling water corrosion damage can provide valuable information regarding the underlying corrosion mechanisms and environmental conditions. Recognizing the different forms of corrosion damage can aid in diagnosis, help prioritize maintenance activities, and inform strategies for mitigation and prevention. Regular inspection and monitoring are essential for identifying these various corrosion forms early, which is crucial for effective management of cooling water systems. Cooling water corrosion prevention and mitigation based on API 571. Number A, cooling water corrosion and fouling can be prevented by proper design, operation, and chemical treatment of cooling water systems. Number B, design for process side inlet temperatures below 140 degrees Fahrenheit, or 60 degrees Celsius. Number C, minimum and maximum water velocities must maintained, particularly in saltwater systems. Number D, the metallurgy of heat exchanger components may need to be upgraded for improved resistance, especially in waters with high chloride content, low velocity, high process temperatures, and/or poorly maintained water chemistry. Number E, periodic mechanical cleaning of tube IDs and ODs should be performed in order to maintain clean heat transfer surfaces. Number F, with very few exceptions, cooling water should be on the tube side to minimize stagnant areas. Preventing and mitigating cooling water corrosion damage is crucial for maintaining the efficiency and longevity of cooling systems. Effective strategies often involve a combination of best practices in system design, material selection, and continuous monitoring. Here are key prevention and mitigation measures. Number 1 is water chemistry control. Number A, of water chemistry control is pH management. Maintain optimal pH levels within the cooling water to minimize corrosive effects. Generally, a pH of 7 to 8.5 is considered suitable for many systems. Number B, of water chemistry control is dissolved oxygen control. Reduce the concentration of dissolved oxygen in cooling water, as it accelerates corrosion. This can be achieved through deaeration or by using oxygen scavengers, such as sulfites. Number C, of water chemistry control is corrosion inhibitors. Use chemical inhibitors that form protective films on metal surfaces. Common inhibitors include phosphates, azoles, and film-forming amines. Number D, of water chemistry control is conductivity monitoring. Regularly check and maintain conductivity levels to avoid scaling and concentration of corrosive ions. Number 2 of the key prevention and mitigation measures is material selection. Number A, of the material selection is corrosion-resistant materials. Use materials that are more resistant to corrosion, such as stainless steels, titanium, or coated metals, especially in critical components like heat exchangers and pumps. Number B, of the material selection is alloy selection. For areas prone to corrosion, select alloys that include elements known to enhance resistance, e.g., molybdenum or nickel. Number 3 of the key prevention and mitigation measures is design considerations. Number A, of the design considerations is minimize stagnation points. Design systems to avoid dead legs and stagnant areas where water can become corrosive and lead to localized corrosion. Number B, of the design considerations is flow velocity optimization. Ensure adequate flow rates to minimize stagnation and reduce the risk of erosion corrosion. Number C, of the design considerations is install proper drainage. Ensure appropriate drainage in areas where water can accumulate to prevent pooling and stagnation. Number 4 of the key prevention and mitigation measures is regular maintenance and inspection. Number A, of the regular maintenance and inspection is routine inspection. Implement regular inspections using techniques like ultrasonic testing, visual inspections, and corrosion monitoring probes to identify early signs of damage. Number B of the regular maintenance and inspection is cleaning programs. Regularly clean cooling systems, including heat exchangers and piping, to remove deposits that can trap corrosive agents. Number C of the regular maintenance and inspection is fouling control. Monitor and control biological fouling, such as algae, bacteria, that can lead to microbiologically influenced corrosion, or MIC. Number 5 of the key prevention and mitigation measures is monitoring and control systems. Number A of the monitoring and control systems is corrosion monitoring systems. Utilize corrosion monitoring technologies, such as electrical resistance sensors or linear polarization techniques, to assess the corrosion rate in real time. Number B of the monitoring and control systems is automated control systems. Implement automated water treatment systems that adjust chemical dosages according to water quality parameters. Number 6 of the key prevention and mitigation measures is cathodic protection. Number A of the cathodic protection is sacrificial anodes. Use sacrificial anodes, such as zinc or magnesium, in systems to protect critical components from corrosion. Number B of the cathodic protection is impressed current systems. In high-risk areas, consider using impressed current cathodic protection, ICCP, systems where traditional methods may not suffice. Number 7 of the key prevention and mitigation measures is educating and training staff. Number A of the educating and training staff is operator training. Train personnel on the correct operation and maintenance of cooling systems, including water treatment processes and corrosion awareness. Number B of the educating and training staff is awareness of corrosion risks. Encourage a culture of awareness regarding corrosion effects among operational and maintenance staff. Number 8 of the key prevention and mitigation measures is environmental and operational considerations. Number A of the environmental and operational considerations is temperature control. Maintain optimal operating temperatures. High temperatures can accelerate corrosion rates. Number B of the environmental and operational considerations is fluid management. Properly manage fluid inclusions, e.g., oils, chemicals, that can affect corrosion rates. In conclusion, preventing and mitigating cooling water corrosion damage requires a multifaceted approach involving proactive management of water chemistry, careful selection of materials, consistent monitoring, and regular maintenance. By adopting these strategies, industries can significantly reduce the risk of corrosion, enhance the longevity of their cooling systems, and ultimately improve operational efficiency. Cooling water corrosion inspection and monitoring based on API 571. Number 8. Cooling water should be monitored for variables that affect corrosion and fouling, including pH, oxygen content, cycles of concentration, biocide residual, biological activity, cooling water outlet temperatures, hydrocarbon contamination and process leaks. Number B. Periodic calculation of U factors, heat exchanger performance measurement, will provide information on scaling and fouling. Number C. Ultrasonic flow meters can be used to check the velocity of water in the tubes. Number D. EC or iris inspection of tubes. Number E. Splitting representative tubes. Detecting cooling water corrosion damage is crucial for maintaining the integrity and efficiency of cooling systems. A variety of inspection and monitoring methods can be employed to assess corrosion rates, identify damaged areas, and inform maintenance practices. Here are some commonly used inspection and monitoring techniques for detecting cooling water corrosion damage. Number 1 is visual inspection. Visual inspection description. Regular visual inspections can help identify obvious signs of corrosion, such as discoloration, rust, pitting, scaling, or biofilm accumulation. Visual inspection limitations. Visual inspection may not detect subsurface corrosion or thin wall failures, it often requires access to all components. Number 2 is ultrasonic testing, or UT. Ultrasonic testing description. This non-destructive testing, or NDT, method uses high-frequency sound waves to measure the thickness of materials. It can identify wall thinning due to corrosion. Ultrasonic testing advantages. provides precise measurements and can detect localized corrosion, such as pitting. Ultrasonic testing limitations, requires trained personnel and may not be effective for highly corroded or rough surfaces. Number 3 is radiographic testing or RT. Radiographic testing description. This NDT method uses X-rays or gamma rays to produce images of the internal structure of components, revealing corrosion and other defects. Radiographic testing advantages, can detect changes in density due to corrosion. Radiographic testing limitations, more expensive and requires safety precautions due to radiation exposure. Number 4 is magnetic particle testing or MT. Magnetic particle testing description. This method detects surface and near-surface flaws in ferromagnetic materials using magnetic fields and iron particles. Magnetic particle testing advantages, effective for detecting cracks and surface corrosion. Magnetic particle testing limitations, limited to magnetic materials and may not indicate overall corrosion severity. Number 5 is dye penetrant inspection or DPI. Dye penetrant inspection description. A dye is applied to the surface of the component, and after a specified dwell time, excess dye is removed. The remaining dye in any cracks or defects is then indicated under ultraviolet light. Dye penetrant inspection advantages, simple and low cost for detecting surface defects. Dye penetrant inspection limitations, limited to surface corrosion and requires clean surfaces for optimal results. Number 6 is electrochemical techniques. Electrochemical techniques. Linear polarization resistance, or LPR, measures corrosion rates by applying a small potential and analyzing the resulting current. This technique provides an instantaneous measure of corrosion rates. Electrochemical techniques. Electrochemical impedance spectroscopy, or EIS, evaluates corrosion characteristics by measuring the impedance of an electrochemical cell over a range of frequencies, providing information about corrosion mechanisms and rates. Electrochemical techniques. Rest potential measurement, measures the open circuit potential of the metal in a corrosive environment, which can indicate the corrosion risk. Number 7 is corrosion monitoring probes. Corrosion monitoring probes description. Probes installed in the system can continuously monitor corrosion rates and report data in real time. Common types include electrical resistance, or ER, probes, measure the change in resistance of a metal as it corrodes. Weight loss coupons. Exposed coupons collect data over time, the weight loss indicates corrosion rates. Galvanic probes, measure the corrosion potential of the environment around them. Corrosion monitoring probes advantages, provide continuous and real-time data indicating corrosion activity. Corrosion monitoring probes limitations, requires installation and may need regular replacement. Number 8 is infrared thermography. Infrared thermography description, utilizes thermal imaging to detect heat patterns and anomalies, which can indicate corrosion and coating failures in insulated pipes and components. Infrared thermography advantages, non-destructive and can cover large areas quickly. Infrared thermography limitations, may require other methods to confirm findings as it is primarily for detecting anomalies rather than measuring corrosion. Number 9 is fiber optic sensors. Fiber optic sensors description, these sensors can be deployed in cooling systems to monitor corrosion and environmental parameters, like temperature and pressure, using changes in light transmission. Fiber optic sensors advantages, allow for remote monitoring and can be very sensitive. Fiber optic sensors limitations, may be costly and require specific installation techniques. In conclusion, a combination of these inspection and monitoring methods often yields the best results for detecting cooling water corrosion damage. Regular assessment helps in identifying potential problems early, ensuring the protective measures put in place are effective, and informing maintenance and repair strategies to extend the lifespan of cooling systems. The choice of method will depend on factors such as the type of material, the environment, accessibility, and budget constraints. Thank you.